We have just discussed sequence of mathematical analysis in details and enumerated their properties in statistical large sample statistical inference. In this module, we shall discuss a concept of series and their convergence and how to check the convergence, and give some applications of series and their convergence in the field of statistics. And lastly, we shall discuss an interesting property of a sequence, because we know that a sequence may either converge or may diverge, but there may be some oscillating sequences, and the nature of oscillation can be enumerated to study the rate of convergence of a sequence. So we have just discussed convergence of sequences. Now we shall discuss in this module another concept which is known as convergence of series and their applications in probability theory and large sample theory. So firstly, a series is a very widely applied concept in statistics. In statistics, or particularly in probability theory, we know Poisson geometric and log series distributions, and it is interesting to observe that each of them is derived from an infinite series. For example, we can look at the identity that minus of log 1 minus theta equal to summation x from 0 to infinity theta to the power x by x factorial for theta lying between open interval 0 and 1, and we get the PMF of log series distribution as probability capital X equal to small x as minus theta to the power x by x factorial multiplied by log 1 minus theta for x ranging from 0, 1 to up to infinity. Next, we shall discuss some basic concepts of series. Let An be a sequence of real numbers. Define another sequence as Sn equal to summation k from 1 to n ak. The pair of sequences An and Sn define an infinite series. So a series is defined by summation n from 1 to infinity An, where An is called the nth term of the series and Sn is called the nth partial sum of the series. So next we shall discuss convergence of series. A series that is a summation n from 1 to infinity An is ordinarily convergent or divergent according as the sequence Sn is convergent or divergent. Therefore, the convergence or divergence concepts of a series boils down to that of a sequence, in particular to a sequence of partial sums. If the sequence of partial sums, that is Sn, is such that limit of Sn exists, with limit of Sn as s, where we allow the possibility of s as plus minus infinity. If s is finite, we say that the series converges ordinarily, and then summation of n, where the range of the summation is from 1 to infinity, is s. However, if s is plus minus infinity, the series diverges, and we say that the series diverges to plus infinity or minus infinity. Now, there are two modes of convergence for a series containing both positive and negative terms. Summation An, that is a series, is absolutely convergent if the series containing the absolute values of the series or the absolute values of An is convergent. That is, summation n from 1 to infinity An is absolutely convergent if summation n from 1 to infinity modulus of An is convergent. Again, summation An is conditionally convergent if summation An is convergent, but summation n from 1 to infinity modulus of An is divergent. Note that absolute convergence implies ordinarily or ordinary convergence. However, the converse is not always true. So let us consider some examples. Consider the series summation n from 1 to infinity 1 by n square. Then the nth partial sum is simply Sn equal to 1 plus 1 by 2 square plus 1 by 3 square up to 1 by n square. Note that Sn is an increasing sequence. Again, we have the inequality that 2 to the power n plus 1 minus 1 is greater than 1, and since Sn is an increasing sequence, the above inequality implies that Sn is less than S 2 to the power n plus 1 minus 1. However, after a routine algebraic manipulation, it can be shown that S 2 to the power n plus 1 minus 1 less than 2 minus 2 to the power minus n less than 2 for every n greater than equal to 1. Thus, Sn less than 2 for n greater than equal to 1, and also by definition Sn greater than equal to 1 for every n greater than equal to 1. Therefore, we find that Sn is monotonically decreasing and at the same time it is bounded. Therefore, by monotone convergence theorem of sequences, we can say that Sn is convergent, and hence the corresponding series, that is the series summation n from 1 to infinity 1 by n square, converges. Next, consider the series with alternating terms, that is summation n from 1 to infinity minus 1 to the power n. Then the nth partial sum is either 0 whenever n is even and minus 1 whenever n is odd. Thus, Sn equal to minus 1 plus minus 1 to the power n whole thing divided by 2. Naturally, Sn is oscillating, and hence according to our convention it does not converge. Thus, by definition the series diverges, and the series also diverges absolutely. That is, if we take the absolute values of minus 1 to the power n, that is 1, then the corresponding series with constant terms 1 is also a divergence series. Next, consider the famous geometric series, that is summation n from 1 to infinity r to the power n minus 1. Then the nth partial sum Sn is n whenever r equal to 1, and it is r to the power n minus 1 divided by r minus 1 for r not equal to 1. If modulus r less than 1, then it is known from the results of sequence that r to the power n tends to 0 as n tends to infinity. Therefore, for modulus of r less than 1, Sn tends to 1 by 1 minus r. However, if r greater than 1, r to the power n diverges to plus infinity, and hence Sn diverges to plus infinity. Further, for r less than equal to minus 1, Sn oscillates. Thus, combining all these, we get that the geometric series converges for modulus of r less than 1 and diverges otherwise, and the geometric series diverges to converges to 1 by 1 minus r. Consider the next example, which is closely related to Riemann's zeta function, and this is known as P series in mathematical analysis. The P series is defined as summation n from 1 to infinity 1 by n to the power p, where p is a real number, and the P series is known to converge if and only if p is greater than 1. Thus, the harmonic series, that is when p equal to 1, diverges. In our next example, consider the series with positive and negative terms, that is 1 minus half, plus 1/3, minus 1/4, plus and so on. It is well known that the above series converges to log 2. Actually, this can be found by expanding log 1 plus 1. However, the corresponding series with absolute values is nothing but the harmonic series which diverges. Thus, we find that the original series, that is 1 minus half plus 1/3 minus 1/4, converges, but the series with absolute values, which is the harmonic series, diverges. Hence, the series is conditionally convergent. In our next example, we shall consider an interesting fact on rearrangement. In fact, the terms of a conditionally convergent series may be suitably rearranged to converge or diverge. Consider the series S equal to 1 minus half plus 1/3 minus 1/4. Naturally, S is log 2 and the series is seen to be conditionally convergent. Now, consider the rearranged series, that is 1 plus half minus 1, that is we are just replacing minus half by half minus 1, then remain 1/3 intact and replace minus 1/4 by 1/4 minus half and so on. Now, separating the positive and negative terms, we get from the above that the above series, the rearranged series can be looked upon as a difference of 1 plus half plus 1/3 etc. minus 1 plus half plus 1/3 etc. Thus, we get that after a rearrangement, we get the value 0. Next, consider the following rearrangement of S by 2. Half minus 1/4 plus 1/6 plus and so on. That is, we have divided S by 2, each term is divided by 2, and we have written this new series S by 2 as 0 plus half minus 0 minus 1/4 plus 0 plus 1/6 minus 0 minus 1 by 8 plus and so on. Now, adding the left hand side with S, we get 3S by 2, and clubbing the different numbers, we get in the right hand side as 1 plus 0 plus minus half plus 1 minus half plus half plus 0 plus 1/3 plus minus 1/4 minus 1/4 and so on. Thus, the right hand side is nothing but 1 plus 1/3 minus half plus 1/5 plus 1/7 plus 1 by 7 minus 1 by 4. That is, the right hand side, in the right hand side we get the same quantity, the same, or the original series is expressed in the right hand side. Thus, we get 3 possible values corresponding to different rearrangements of a conditionally convergent series as log 2, 0 and 3 log 2 divided by 2. For a detailed discussion and the related theory on this issue, we refer the reader to the methods of real analysis by Goldberg. So, let us enumerate the application of conditionally convergent sequences, conditionally convergent series in probability. The above observation or the above property of rearranged series forms a basis to define the existence of moments. Suppose x is a random variable with probability mass function probability x equal to xi as pi, then for some function g, expected value of gx is said to exist if and only if the series summation gxi multiplied by pi is absolutely convergent. Now, we shall give an example to show that the usefulness of above requirement. Suppose xi is minus 1 to the power I minus 1 multiplied by 2 to the power I by I, and pi is taken as 2 to the power minus I. Then it is easy to observe that the series summation xi pi, which is nothing but minus 1 to the power I minus 1 divided by I, is ordinarily convergent and converges to log 2. However, the series is not convergent absolutely, because when we take the absolute values of xi multiplied by pi, we get 1 by I, and therefore the series with absolute terms is nothing but the harmonic series which diverges, and hence according to our definition, expected value of x does not exist even though summation xi pi is convergent. Another application of convergence of series is to check the existence of moments of distributions which support as a whole set of integers. For example, consider probability x equal to small n as c by n into n plus 1, where n ranging from 1 to up to infinity and c is a positive constant. Naturally, c is such that summation probability x equal to n equal to 1. Now consider the nth partial sum of the above, which is Sn, and defined as summation I from 1 to n c times 1 by I into I plus 1. Now just adjusting 1 by I into I plus 1 in partial fractions, we get that Sn equals c multiplied by 1 minus 1 by n plus 1. Thus as n tends to infinity, we get that 1 by n plus 1 tends to 0, and hence Sn tends to c. Thus we get summation n from 1 to infinity probability x equal to n equal to 1 only when c equal to 1. However, we find that the series summation n from 1 to infinity n multiplied by probability x equal to n diverges, because in that case we get the series summation 1 by n plus 1 which is a divergent series, and hence expected value of x does not exist. Next we shall introduce the concepts of supremum and infimum of a sequence. We have already seen that the sequences can diverge. However, the asymptotic behavior of a divergent sequences or divergent sequence can be described by considering the behavior of the bounds of the sequences. For a sequence, L is a lower bound if an greater than equal to L for every n greater than equal to 1, and U is an upper bound if an less than equal to U for every n greater than equal to 1. From the properties of real numbers, if a sequence admits a lower or upper bound, it also has a greatest or least lower or upper bound. The least upper bound and the greatest lower bounds are defined respectively by UL, which is defined as supremum of an, and LU as infimum of an. The limiting behavior of any sequence can be studied from the behavior of these bounds for increasing n. Next we shall discuss an interesting concept which is known as limits of the bounds. Note that supremum over k greater than equal to n, an is a decreasing sequence, and hence we get the limit as infimum of supremum of an. The above quantity is known as a limit superior of an and is denoted by either lim sup an or limit upper bar an. Again, infimum of an, where the range of infimum is k greater than equal to n, is an increasing sequence, and we get the limit as supremum with range n greater than equal to 1 of infimum of an, where the range of infimum is k greater than equal to n. The above quantity is known as limit inferior of an and is denoted by either lim inf an or limit lower bar an. Unlike limits, these two quantities always exist and can be used to judge the behavior of a sequence in the limit. So let us discuss some properties. A sequence an is convergent if and only if the limit superior and limit inferior are both finite and equal. For any sequence an, limit superior is always greater than equal to limit inferior. If limit superior is finite, then limit superior of an is nothing but minus of limit inferior of minus an. If an and bn are two sequences with finite limit superior and limit inferior, then limit superior of an plus bn is less than equal to limit superior of an plus limit superior of bn, and the limit inferior of an plus bn is less than equal to, and limit inferior of an plus bn is greater than equal to limit inferior of an plus limit inferior of bn. If an and bn are two positive sequences with finite limit inferior limit superior, then we get limit inferior of an bn, the product is less than equal to the product of limit superiors. So, let us consider some examples. Consider an equal to e to the power minus n. The sequence is strictly positive and monotonically decreasing in n. Now, supremum value of ak for k greater than equal to n is nothing but the supremum value of e to the power minus k for k greater than equal to n, and since e to the power minus k is a decreasing sequence, we get this supremum as e to the power minus n. Naturally, limit superior of n is nothing but the infimum of e to the power minus n for every n where the infimum has range n greater than equal to 1, and we get that this infimum is nothing but 0. Again, infimum of ak for k greater than equal to n is nothing but the infimum of e to the power minus k for k greater than equal to n, and which is again 0. Thus, limit inferior in this case is also 0. Since we get limit inferior and limit superior both finite and both 0, that is equal, we observe that the limit exists, and this limit is given by limit of n equal to 0. Consider our next example where the sequence is taken as 1 plus minus 1 to the power n, and the sequence is naturally non-negative and oscillates between 0 and 2. That is, the value of an is either 0 or 2. Now, supremum value of ak for k greater than equal to n is nothing but 1 plus supremum value of k greater than equal to n of minus 1 to the power k, which is 2. Therefore, limit superior is nothing but 2, and in a similar way, the infimum value of ak for k greater than equal to n is 0, and hence we get that limit inferior of n is 0. Thus, we find that here limit inferior and limit superior are both finite, but they are different. Since these two quantities are different, limit does not exist. So, we have just seen what is a series and what are their roles in statistics and especially in probability theory, and we have also seen that how different equations of first order or some different orders can be enumerated numerically in the large sample using the concepts of limit superior and limit inferior of sequences. And in our next module, we shall discuss different tests of convergence for positive series and for alternating series and their application in statistics.